Hello everyone. So previously we had discussed on the segment tree algorithm, right? So today what we'll be saying, today we'll be discussing on the topic lazy propagation and the segment tree. So we have idea on the segment tree algorithm, right? So how it works, what are the things where it is applicable, when we have to make use of the segment tree, these kind of things we have already seen, right? So now let's discuss the lazy propagation and segment tree. Let's see what is lazy propagation and where we can make use of it. Basically, how we can optimize it by how we can optimize the segment tree by making use of the lazy propagation. Those kind of things we'll be discussing within the lazy propagation and segment tree algo, right? So let's see what the definition part say here. Let's get into the definition part first. So here, lazy propagation is an optimization technique. Basically what it is an optimization technique used in the segment trees, right? Lazy propagation, it is an optimization technique used in the segment trees to efficiently perform range updates, right? So lazy propagation is an optimization technique used in the segment trees to efficiently perform range updates. See here, updating a range of values at once, right? So we know this. So without updating every element immediately, right? So without updating every element immediately, right? So what it does, basically what does lazy propagation does? So the term lazy propagation itself indicates that it delays or lazily propagates this one, updates to child nodes only when necessary, right? So it delays or lazily propagates updates to the child nodes only when necessary, right? So that one will be seeing when we write the code as well, right? So just remember this, right? So improving performance from big of n per update to big of log n, right? So it improves the performance from big of n to big of logarithmic n, basically, right? So this we know. So we make use of the lazy propagation in the segment tree when we need the intense optimization, right? Even intense optimization, we make use of the segment tree itself for the intense optimization. We make use of the lazy propagation in the segment tree for the extreme, this one, or when extreme optimization is needed, right? So just remember, so usually when we implement the segment tree on certain problems or the certain contest, basically whether it may be lead code or the code forces, right? So usually it will be, mostly it will be the last two problems, right? The last two problems when it is extremely difficult to implement in the given point of time, right? So usually segment this one, lazy propagation, we make use of it when extreme optimization is needed. Just remember this one, right? Let's get into the explanation part. So in the normal segment tree, updating the range of elements requires updating multiple nodes, right? So in the normal segment tree, updating the range of elements requires updating the multiple nodes, causing big of n complexity in the worst case. So with the lazy propagation, each node carries an extra lazy value that stores the pending updates. So with the lazy propagation, what happens? Each node carries an extra lazy value that stores the pending update. So this is the main difference. These two things, whatever I say, this is the main thing. See here, with the lazy propagation, see, in the normal segment tree, we are updating the range of elements requires updating multiple nodes, right? Just causing big of n complexity in the worst case, right? So usually this one, update as well as the querying we will be going with the big of logarithmic n itself and the segment tree as well, right? So with the lazy propagation, what happens? Each node carries an extra lazy value that stores the pending updates as well, right? So when we visit a node, if it has a pending update, we apply it to the current node and propagate the update to its children lazily. So that's what we'll be doing. So if you didn't understand this one, we'll be implementing the same thing in the form of code. Don't worry, right? In the form of algorithm by making use of this one, Python programming language. We don't have to worry for now, right? So this means updates and the queries both work in big of logarithmic n time. Again I'm stressing on this, updates and the queries in the lazy propagation and segment tree work in big of logarithmic n time complexity, right? So let's discuss the use cases. So this lazy propagation and segment tree, basically, so this can be used for the range sum updates, range maximum and minimum updates, this one, as well as interval assignment problems, as well as interval assignment problems, right? So what happened to this one? Why this turned into the blank one? Close this one. Yeah, just 1 second. So now we know the use cases as well, right? So range sum updates, range minimum maximum updates, interval assignment problems, right? So let's do one thing. Let's start writing let's implement the same thing whatever we have discussed in the explanation, right? So let's implement the same thing in the form of algorithm, same thing in the form of code or the algo, right? So we'll be making use of the Python programming language. So let's go with the lazy propagation and the segment tree for the range sum query, right? So first we'll be going with the build. Basically let's build the segment tree first. So I'll just go with class segment tree here. This is fine. Within this class I'll just go with the initialization part or the constructor part. Let me go with init. So yep, so let me remove this one. Along with the self I need array as well, right? So this is fine. So within the init constructor part I'll just initialize into length of the array. Let's go with the length of the array. Also I'll just go with self.tree equals 0 into this one, basically 4 into n. This is fine. Next part would be, let's go with the lazy array for the pending update. So this one will be dot lazy, this is fine, equals 0 into I'll just go with 4 into self dot n. This is fine. We are just going with the lazy array for the pending updates. Finally let's go with the recursion. So I'll just go with the recursion. Basically basically will be we have to go with the build, and we haven't built the this one. Basically we haven't built this one segment tree, right? So initially, before making use of it within the constructor part or within the initialization part, let's build the tree recursively first, right? So I'll just go with def here, with the name I'll just go with build. So let me go with self array. So we need I along with the left and right. So this is fine. So within the build function, so if left equals right, then what we need to do, so we have to go with the leaf node that stores the actual array value, meaning here I'll just go with the self dot tree of I. Let me assign this one to the array of I. This is fine, man. Yep. Sorry, array of I. No, this is left, right? So we are assigning this one to the array of left. Yeah, array of left basically. Then I'll just give here a return, right? So this is fine, man. Now let's do one thing. We have to calculate the mid. So we know that segment tree is a binary tree, right? That is pure basics basically. Right? So this one will be left plus right by 2. We are just calculating the mid. So I'll just go with self dot. So I'll just go with builder here. So this one will be array comma 2 into I. This is fair. Also left, we are going with the left one, right? So this one will be mid left. So same thing will be going with the right. So did I give builder here? So this has to be build, right? So we are going recursively here. So again, let me go with self dot build. Why this is not showing? Oh, underscore build I have considered here. This is fine. Let's go build. So this one will be array comma. So we are going with a right subtree. So this one will be 2 into I plus 1 for the right one. So we'll be moving right side from mid plus 1. So this one will be mid plus 1 comma right we have to mention. So we are doing it recursively, right? So finally we have to combine the result. So I'll just go with self dot tree here, self dot tree of I. This is fine. So this one will be self dot tree 2 into I, so this one has to be 2 into I, along with the self dot tree here. This is fine. This one will be 2 into I plus 1, right? So we are just combining the results here. This is fine, man. So the next step here would be, let's go with, we have made use of the build, I mean we have already written the build function here. So let's go with self dot this one here, build, right? So here what are the parameters that we need to pass? Array followed by, let's start with a 1, 0, and also n. We need n as well, right? So n, so we have to go until n minus 1, the last one, n minus 1. Okay, so this is fine, self dot n minus 1, right? So this is fine, man. Now we have successfully went with the initialization part, constructor part, as well as the build, right? So building the segment tree, we are done with this part. Now let's do one thing. What shall we do? We have successfully built the tree recursively. Now let's propagate any pending updates, right? So I'll be making use of the function push basically. So I'll just go with underscore push. So what are the parameters that we need here? So here I need self, so this one will be I left comma right. So this is fine, I believe. The next thing here would be within the push function. So let's write the simple if condition. If lazy, so I'll just go with the lazy here, lazy of I, if it is not equal to 0, then what we need to do, we have to apply the pending update, right? So that's what we discussed in the explanation as well. So we are propagating any pending updates here, right? So we have to apply the pending update. That is the reason I have considered here, meaning so in the if condition I have written lazy of I, if lazy of I not equal to 0, right? So then we have to apply the pending update, right? So this one will be, so tree of I equals tree of I plus this one right minus left plus 1 into lazy, this one lazy of I. This is fine. Now let's do one thing. Let's write one more if condition. If not the leaf, then we have to mark the children as lazy, right? If not the leaf, then what we need to do, we have to mark the children as lazy, right? So I'll just go with if here left not equal to r accordingly with the explanation. So here I'll just go with, we have to mark the, if not leaf, we have to mark the children as lazy, right? So this one will be lazy of 2 into I, what's lazy of 2 into I plus lazy of I basically, right? So this is fine. We have to mark the children, both the children, left and right. So we have went with the left, we have to go with the right as well. So this one will be lazy of 2 into, for the right will be going with the I plus 1, right? So this will be lazy of 2 into I plus 1 plus this one lazy of I. So this one will be lazy of I. This is fine. Finally what we will be doing, so we have to clear the lazy value after the propagation, right? So this one will be lazy of I. We have to, in simple terms, we have to assign the lazy of I to 0, meaning we are clearing the lazy value after the propagation here. This is fine. So let's do one thing now. After the push function, let's go with the range update here. When I say range update, we have to add the value to all the elements in the range. This one, query left comma query right will be considering. In simple terms, we'll be going with a QL comma QR here, right? So let's go with the update, this one, update function. So this one is fine. So this is completely related to the pure segment tree. So this one will be update. So we need here self I, also left right. So query left, query right. So this one will be value. Simple, right? So within the update function, first thing we have to first apply any pending updates. if any pending updates, then we have to first apply that one, right? So I'll just go with self dot we have already written push function, right? So I'll just go with push here. So I'll just go with I comma this one, left comma right. This is fine. Now if there is no overlap, then we have to exit from there, right? So if QR is less than L, query right, oh A I have considered here, that is the reason this is screaming here. If QR less than L or query left, this one greater than R, then what we need to do, we have to exit, right? So I'll just give here return. This is fine. Next step would be we have considered when no overlap. If total overlap occurs, if there is total overlap, then what we need to do, we have to mark the particular node as lazy and we have to apply immediately to the current node. That's what we need to do, right? So when there is total overlap, let me go with a simple if condition. When we have total overlap, meaning QL query left, if it is less than or equal to L, and right if it is less than or equal to query right, then what we need to do, we have to mark the particular node as lazy, right? So I'll just go with lazy of I here is equal to lazy of I plus value, right? So no confusion. Next we have to apply immediately to the current node as well. So this one will be making use of the push function that we have already written, right? So I'll just go with same thing, I left as well as the right. This is fine. Finally we have to exit from here, so I'll just give the return. This is fine, man. Now we know that the cell this one segment tree is a binary this one tree. Let's move on with calculating the mid basically. So this one will be left plus right by 2. This is fine. And so let's recursively update here, right? So this one initially for the left one, so this one will be 2 into I comma mid, so this one will be query left, so this one will be query right, and finally this one will be for the value. Then let's go with this one update. So this one will be for the right one, so we'll be going with the I plus 1, 2 into I plus 1 comma mid plus 1 we have to consider. So this will be right. Also we have to go with the query left, we have to consider query right as well, along with this one value. So this is fine. The final step would be we have to update the parent node. So here I'll be going with a tree of I. So tree of I will be equivalent to so we have to update the parent node, right? So this one will be tree of I, this one we have to consider left and right both. So this one will be 2 into I, subtree tree of 2 into I, plus we'll be going with the right one, right leaf as well, right subtree as well in simple terms. So this one will be tree. So this is not showing in this one man correctly in the suggestion. So this one will be 2 into I plus 1, right? So this is it for the update function, right? So update method of the function. Next what we'll do, let's go with this one. What do we call, we are done with the update. We need to go with the query as well, right? So we are going with a range sum query. We have considered the example, this one basically for the range sum query, right? For the range sum query, so we have to go with the query method as well. We have to go with the query method of the query function as well. So let's go with the range sum query here. Yes, so I'll just go with query here. So I need the parameter self, so I left right query left as well as the query right. Simple. Yep. The next part would be so we have to apply the pending updates before querying, right? So I'll just go with the push again. So this one will be push again I comma L comma R, right? So this is fine. Now when there is again the same thing we did in the update, right? So when there is no overlap, so if query right is less than the left, or query left greater than r, then if there is no overlap, then we have to exit. So I'll just give return here. So when there is total overlap, then what we need to do, if ql less than or equal to l and r less than or equal to query right, then what we need to do, we have to return this one iterated value of the tree, meaning I'll just go with self dot tree of I. So this is fine, man. The next step would be, let's go with the this one. Segment tree is the binary tree, so we have to calculate the mid. So mid equals left plus right by 2. This is fine. Let's go with the left sum here. So this one left sum equals self dot query. So this is fine. This one will be 2 into I. This is also fine, comma left, comma so this one will be mid, query left, comma query right. So this is fine, man. Again, so this will be right sum. So I'll just, yeah, let me assign this one to the self dot. So we are recursively doing this one, right? So I'll just go with query. So this is not showing in the suggestions, why I don't know. Self dot query. So this one will be 2 into so we are going for the right subtree, right? So this one will be 2 into I plus 1, comma mid plus 1. Also we have to go with the right. We need query left and query right. So this is fine, man. Finally we have to combine the result. So I'll just go with the return left sum along with right sum. So I'll just go with left sum along with the right sum, right? So we are just combining the results here. So this is it for the query this one method or the function, right? So we are done with the algorithm. So this is it. Basically I have explained you every step, right? So we have went with 4 functions. Basically one is building the segment tree, then we have went with the push. So what is push? Basically I had explained earlier itself. So we are just propagating any pending updates within the push function or the push method, right? So now this one update, within the update, what we are doing, we are just going with a range update, meaning we are adding the value to all the elements in the range, query left, comma query right, nothing but ql comma qr, whatever we have considered, right? So now within the query function or the query method, what we are doing here, we are just going with a range sum query here, right? Simple. So we are done with the algorithmic part. So next what we will be doing, so we have to go with the example usage, right? So we'll be making use of the print. So we have to go with something, we have to show something, right? So we have to consider the input and this one, for that we have to get some particular output just for the interactive purpose. So let's go with the example usage here. So let me consider array equals some random numbers, easy one, a 1 2 3 4 5, right? So let me go with 1 2 3 4, right? So we are going with the segment tree. Let me call the segment tree class here, segment tree. Let's pass the array, this one, right? So this is fine. Now let's make use of the print statement for the interactive purpose. So this one will be initial sum of range. So this one I'll just give 1 comma 3. This is fine. This is segment tree dot query. This one will be query dot query of 1 comma 0. So this one will be segment tree dot n minus 1 comma 3. This is fine, man. I'll just go with segment tree dot update. So this is fine. 1 comma 0 segment tree dot n minus 1. This is also fine. 1 3 comma 2. So this is also fine, man. Now let's go with the print statements here. So this one will be print after adding, so this one plus 2 to range. So this one will be 1 comma 3 sum of 1 comma 3 this is fine. 1 comma 3, this one I'll just go with a segment tree dot let me go with a query actually, segment tree dot query. So I'll just go with some starting from 1 0 as well as segment tree dot n here. Let me go with n minus 1, sorry, not n here. So this one from the range 1 to 3 basically, this is fine, 1 comma 3. Now let me make it of one more print statement here. So this one will be final sum of full array. This one we go with segment tree dot query. So again, so this one will be 1 comma 0. I'll just go with segment tree dot n minus 1 again until n minus 1. So I'll just go with 0 comma 4. This is fine. So this is just for the interactive purpose. I've considered the input, right? So the output that we need to get here is, so we are considering the range from 1 to 3, right? So see here this part, line number 80, right? So we are considering from 1 to 3. So the initially what output that we need to get here, so initial sum of the range we are giving, right? So see here, initial sum of range, so I'll just keep capital I here, initial sum of range from 1 to 3. So we are going with 1 2 3 4 5, 1 2 3 4 5. So this one will be, just give me a second here, accordingly with the segment, whatever this one we have written code or the algo we have written. So this one 0 1 2 3 4 basically. So we are going from 1 2 3, we are going with a range sum query, right? So but 4 plus 3 is nothing but 7, 7 plus 2 is nothing but 9. See here, from the range 1 to this one, 1 2 3, we are going with a range sum query. So this one has to be 2 plus 3 plus 4, in this case it has to be 7 plus 3, this one 7 and 9, right? So initially the output that we need to get here is 9. So because we are going with the initial sum of range, this one, this part, line number 78, right? So let's go with the this one. Next what we are giving here, this one, after adding plus 2 to the range, right? So after adding plus 2 to the range, this one again we are going with a 1 to 3 itself, right? 1 to 3 basically. After adding plus 2 to the range 1 comma 3, the sum of this one, sum of this one, what do we call, from range 1 to 3 has to be this one, 15 basically, right? So it has to be 15, right? So final sum of the full array would be, so if you sum up this one, we are going with the final sum of full array, right? So this one basically, so this one has to be, we have considered the array 1 2 3 4 5, right? So the simple one, so this one has to be 1 plus 2 plus 3 plus 4 plus 5, right? So this one 5 plus 4 9, 9 plus 3 12, 12 plus 2, this one has to be 12 plus 2 14 plus 1 15, and we have considered plus 2 here somewhere, right? So we are adding plus 2 to the range. So this one basically this one 0 to 2 we have to consider, right? Plus 2. So this one has to be 3 plus 2 plus 6 again. So 15 plus 6 we have to go with. So the final output that we need to get here is 21. Here also we got 15. After adding plus 2 we got this one, what do we call, 9 plus 6 we will be going with. So this one will lead to 15, the range from 0 to 2 plus 2 we have added here for this one, right? So this one will be 9 plus 6 15 itself. So here the sum of all the elements initially it will be 15. So 15 adding 0 comma 2 again, 0 to 2 interval again, so that would lead to 1 plus 2 plus 3, this will lead to 6 basically. 15 plus 6 would lead to 21. So this would lead to 21 and this would lead to 15. Yeah, this would lead to 15 basically, right? So let's check the same. So I have already explained the algo. This is simple one, man. Code looks somewhat, this one lengthier, code is somewhat lengthier basically, but if you understand this one, this is very easy basically, I wouldn't lie, right? So this is fine. So I'll just give Control J here, and also let me copy this one entire file name basically. So Control J, this is not working. Yeah, this is fine. We give clear screen here. So I'll just give Python followed by file name .py. So we are getting the error. Segmented object has no attribute build. Line number 32. We have went with, so that is the reason we are getting error. So we are going with basically, just give me a second here. Underscore build we have went with, this is correct itself, right? What's wrong here? Def underscore build, this is the name that I have given, so this has to work correctly, no worries. What's wrong? I am not able to understand. No. Line number 7, 6. Let's check one more thing here. Let's check what we have done wrong. So yeah, what mistake I have done here is indentation, this one problem basically. So these are the functions which should be at the same level, right? So this will quite obviously give the wrong answer. So we are writing the function, all the functions, push, update, query within the this one initialization or the constructor part, right? So that would obviously, that will throw the error. This is fine. Now this has to work. Let's see. So we still have the error here. What is the error basically? Unsupported operand types. Type and int. This one, line number 73. So let's check what is wrong here. This is correct itself. Just give me a second here. So within the this one update method or the update function, so what I have done here is, so I have not mentioned a left at all here. This one for the left subtree. So we are recursively going with the left for the left subtree, right? So this one I have given 2 into I, mid I have given directly basically. After the 2 into I, this one I have to mention left, right? So here this one, this will throw the error quite obviously. So this is one of the errors. So let me run this one again. So we still have the error. So this is one of the things basically, line number, just give me a second here. So in the query function or the query method, so we are going with two conditions, right? So when there is no overlap, when there is total overlap, and when there is partial. So for the no overlap we have to return 0. So we are just exiting directly here. So that is the thing that we are doing wrong. So I have just given a return here. So right, so I have to give a return 0 here. So this has to work now. Let's see. So yeah, we are getting the still we have something wrong here. Segment tree dot update takes 7 positional arguments, but 1 is given. So where line number 79 here, it takes 7 positional arguments, right? So what I have given here, 1 where it is 1 comma 0, this is fine. Segment tree, this one n-1, this is also correct. Then 132, yeah, extra 1 I have given here. Sorry, this one has to be 132, right? So this is fine, man. Now this has to be correct. Let's see. Yep, we are getting the output 9 initially, right? So initial sum of the range from 1 to 3, it has to be 9 itself, right? So this one 1 2 3 we are considering. So I have already explained this one. 4 plus 3 is 7, 7 plus 2 is 9. We are getting the correct output after adding plus 2. So we are adding the plus 2 range, meaning from 0 to 2. So this one we have to consider from 0 to 2, right? So after adding plus 2, the range 1 comma 3, sum from 1 to 3 is basically, so this will be this one 2 3 4 9 9 plus 6, it will be 9 plus 6, it would lead to 15 basically, right? So 1 2 3 we have to add from 0 to 2 per range we have to consider. So that would be 9 plus 6. So this is fine. Finally, final sum of full array would be, so initially it was 5 plus 4 9, 9 plus 3, it would be this one 9 plus 3 would be 12, 12 plus 2 14, 14 plus 1 15, 15 plus we have added plus 2, nothing but it would lead to 6, 15 plus 6 would be 21, right? So the final sum of full array would lead to 21. So we are getting the desired output, right? So initial sum of the range, again I'll explain the same thing, don't get confused here. Initial sum of the range, so here so just give me a second here, 1 second, where did I take the input? Yeah, arrays here, right? Initial sum of the array, this one. So from 1 to 3 we are considering from 1 to 3 index, right? So this one is 0, index 0, 1 2 3 4. So we have to consider 1 2 3 here, this part, meaning 2 3 4. So when we add 2 3 4 it would lead to 9, right? 4 plus 3 7, 7 plus 2 9. So this is fine. So now after adding plus 2 range, the array becomes basically, so see here, plus 2 you can consider 0 to 2, or we can consider in this way, plus 2 to the range means, so we have here 1 2 3 4 5, right? So plus 2 we are adding to the range 1 2 3, 1 2 3, right? So this is index 0 1 2 3 4. So we are adding plus 2 to the range from 1 to 3, meaning, so we are going with plus 2 to this one. So this becomes 4, 2 plus 2 4, 3 plus 2 this becomes 5, and this becomes basically 6, 4 5 6, right? So this one will be 1 4 5 6, or we can directly consider from 0 to this one, right? So that is also fine. So here array becomes 1 4 5 6, and finally we have 5 as well, right? So this one will be 5. The array becomes 1 4 5 6 5, right? So the new sum of indices, from 1 to 3, so this one is 0 1 2 3 4, right? So we have to sum up from 1 to 3, so we have to go with 4 plus 5 plus 6. So this would lead to 4 plus 5 plus 6, so this will lead to 6 plus 5 11, 11 plus 4 15, right? So this is fine, 15, right? So this is fine. Finally will what we are going with, so final sum of full array, right? So this one will be this thing, we are going with the final sum. So this one will be 1 plus 4 plus 5 plus 6 plus 5. So this would lead to basically 5 plus 4 9, 9 plus 1 10, 10 plus 6 16, 16 plus 5 21. So that is how we got the output 21 here. For this one we got 15, and for this one we have got 1 plus 2 plus 3 plus 4 plus 5. Initially it is this one 1 2 3 we have to go with, 2 plus 3 plus 4 we have got 9, this one, right? So that is how we got 9 15 as well as the 21 as output, 9 15 and 21, right? So this is it for the basically lazy segment, lazy propagation in the segmentary part algorithm, right? So this is simple, I believe, right? So this is it for the lazy propagation and segmentary algorithm. So we are done with the algorithm. So let me summarize whatever we have learned so far, so that we can move into the next algorithm tomorrow, right? So we are done with the lazy propagation and segmentary algorithm, right? So tomorrow we'll be going with a persistent segmentary algorithm, right? So this will be the last algorithm on the segment tree basically, right? So not the tree based algorithm. So this will be last algorithm on the this one, segment tree, that involves segment tree basically. The next one will be discussing on the persistent segment tree algo. So now we are done with the lazy propagation and the segment tree algorithm. So let me summarize whatever we have learned so far. Just try to remember these 2 to 3 points or 3 to 4 points, right? So here lazy propagation is used to efficiently handle range updates on the segment tree. So this is the first point. Lazy propagation, it is used to efficiently handle the range updates on the segment trace. So what it does, it stores the updates lazily. So it stores the updates lazily. That's what it does, lazy propagation, right? It stores the updates lazily and applies them only when necessary. It applies them only necessary. It's saving the time basically. It saves a lot of time, right? So both range update and range query operations achieve because of logarithmic and time complexity. So both this one, range update as well as the range query, right? Both range update as well as the range query operations achieve big of logarithmic and time complexity. It's widely used in the competitive programming. So we that's what I wanted to say. Usually it's widely used in the competitive this one programming and interval based optimization problems. When interval based optimization is needed, intense optimization or extreme optimization is needed, we'll be going with a lazy propagation, right? So yeah, this is it. These are some of the points that we need to remember at any cost. So this is it for the lazy propagation and segment tree algorithm. Next, as I have said, we'll be discussing on the persistent segment tree algorithm. For now, this is it. Thanks for watching, guys.